Hello AP Physics C students. So here's a problem that I want you to solve in your notes. So make sure you have your handwritten notes open. You don't necessarily have to copy down the entire body of the problem, but you definitely have to copy down this diagram. So take a second, read the setup of the problem, copy down the diagram, and then I'm going to tell you what we're going to be doing. Okay, so first of all, this is a little bit different from problems we've done before. So far we've been looking at a conducting rod sitting on top of conducting rails. We're looking top down at it. We're looking down at the situation so it's free to rest on the rails. This is different. In this situation, we're looking at it from the side view. We're letting this conducting rod fall, and it's going to fall here. And I've drawn little loops here saying that it's sort of sliding along these rails. It's touching them. It's always in contact with them, but the rails are frictionless, and so the whole system forms a conducting circuit. And it's all sitting inside a magnetic field with all these dots here representing the field pointing out of the page. So this is fundamentally different from what we've seen before, but certainly, obviously, connected to things we've done before. So here's what we're going to be doing. Here's all the parts of the problem. Go ahead and read all this. You don't have to write it all down. We'll be doing it step by step. Just get a sense of what we're doing. Now, in the end, really, we're trying to solve this. We're going to get a differential equation, and then we're going to solve it for the speed of the rod as a function of time in terms of all the variables defined. Really, in fact, I could have just given you this problem here and then asked you to go and solve, but I'm breaking it down step by step, as they might do on the AP exam. And we'll take it step by step. In fact, we'll take it step by step. I want you to try it on your own, pause the video as you do so, then come back to see it. Really, that's the best way of doing it. All right, so let's start with part A here, just labeling the ends of the rod as either positive or negative. So pause the video, do what you need to do to figure that out, and come back to see how I do it. Okay, so we should have been getting that the left end is positive, the right end is negative. And I do it two different ways. First, we can look at one of the individual mobile protons inside the rod. That's one of our standard ways of looking at it. And the proton is falling down because the whole rod is falling down. So here's its velocity vector. It's sitting inside a magnetic field pointing out of the page. So using our right-hand rule, we should be getting that the magnetic force on this individual proton is to the left, which means all the protons in the rod, not all of them, but some of the protons are going to be forced to the left end, making the left end positive and the right end negative. Next part has to determine the direction of the induced current to the rod. Now, there's actually a completely different way of doing this, and so if you had used Lenz's law, you probably did part B first, then part A second. I'm going to go through that solution in just a second, but I want you to either have done parts A and B all on your own using this method or Lenz's law before you come back to see how I do it. Okay, so if we're using this method, now this end is like the positive terminal of the battery, this end is like the negative terminal of the battery, which means charges are going to flow out of this end through the resistor, back in here, and to the left inside the rod. So we should be getting a current pointing to the left. Now, if you didn't do it this way, if you did it with Lenz's law, here's how that should look. So starting actually from part B, for figure out the direction of the current first, we do our usual steps here. The initial direction of the field, the change in the field, the induced field, and the current. And if you were starting Lenz's law, if you didn't do it this way, this is how you should be starting. Alright, so initial direction, the field obviously is out of the page. We're moving the rod down, so we're including more of these field lines out of the page. And so that means the field is going to be induced into the page, right? The universe hates change. And so if you put more field lines out of the page by moving this rod down, then the universe is going to say, well, we got to get rid of those by inducing a field into the page. Using our right-hand rule shortcut, you should be getting that the current throughout the loop should be pointing in a clockwise fashion. And if it's going around in a clockwise fashion, then certainly the current is pointing to the left inside the rod. And that means that this end is positive and this end is negative. So we get the exact same solution either way, by looking at the individual mobile protons or by doing Lenz's law. Alright, part C here is drawing a free body diagram of the rod after it's picked up some speed, because I did say it's let go from rest, and so nothing interesting is going to happen at the moment it's let go. So just, a little bit of time later, go ahead and draw the free body diagram, pause the video, and draw that. Okay, we always, of course, start with weight down. Remember, we are looking from the side, so mg points it straight down. And now that it's picked up some speed, and now that there's a current in the rod, there's going to be a magnetic force. And so, of course, we do our right-hand rule. Now, which right-hand rule is it? Is this the point, or the grab, or the shortcut? Ooh, we got all sorts of choices here, right? Remember, anytime we deal with forces, it's the pointing. So our right hand, our finger points to the left, our fingers curl out of the page, and so our thumb is pointing to the top of the page. And this should make sense. Every time you've seen these sort of problems, we know that the magnetic force is always opposing what's happening. And so as the rod is falling and it's creating a current, the universe says, well, we don't want that to happen, so it's going to try to slow it down by opposing it. But we get that from the right-hand rule. Alright, now we get to part D, writing a differential equation to describe the motion of the rod as it falls. So, pause the video, do as much as you can on your own, and come back to see what I do. I'll give you some hints along the way. Okay, differential equation, if you don't remember, sounds a little bit scary, but it's really not. It just means we have to get something that has a derivative in it. And so, as always, we start with sigma f equals ma. So, if you didn't even know where to start, and you didn't start with sigma f equals ma, well, start with that, and then see what you can do on your own. Pause the video again, see if you can do more of it on your own before you come back to see how I do it. Okay, so we have to get a differential in there, which means we're going to write a as dv dt. And of course we have mg down, f epsilon up, mg is going to win, so it's mg minus f epsilon equals m dv dt. Now, if you stop right there, you've actually satisfied the problem. It's not really the best version of it, because it's not in terms of really what's happening here. But if you stop right there, you couldn't be faulted. But we really want to put this more in terms of the symbols and the variables that are given in the problem. So first thing we want to do is replace f sub m with ILB sine theta. Certainly we're not looking at the point charge, we're looking at the entire rod. It's a wire with a current, so it's ILB sine theta. But current is never defined in the problem, so we want to replace current. So we're going to use Ohm's law. I equals EMF over R. It could be delta V over R, but remember it's an induced EMF in the rod from one end to the other. It's a motional EMF because it's just like other problems we know with motional EMF, so EMF equals BLV. So we put that in here, so here's BLV over R, put in for I. Theta is going to be 90 degrees, as it almost always is, so sine 90 goes away to 1, so we got rid of the sine 90. And then we just collect some terms. Here's B times B is B squared, L times L is L squared, and I wrote it out like this so that we're looking at a term of V and a term of dv dt. And this is, I'd say, a better version of the differential equation because it leads us to the next step. Alright, the next step is to find the terminal speed of the rod, V sub t. So pause the video, solve for that, come back to see what I do. Okay, terminal speed, that means it stops accelerating, so dv dt equals 0. We're going to replace v with v sub t. So this whole side is 0, put this to the other side, we just solve for vt, we should be getting this term mgr over b squared L squared. Okay, so now we're finally ready to do the last part, which really would have been like the first part if I just gave you this problem, is just solve for an equation for speed. So here's the equation we just developed. And now I want you to see how far you can get. I will give you a hint that you are allowed to use v sub t, and that might make your solution a little bit easier. I'll also give you another hint that back when we've done other problems like this, we had used a u substitution at some point. You don't necessarily have to do that, but I think it makes it a little bit easier. So do as much as you can on your own. Then come back to see what I did. Okay, now this is going to take quite a lot of room, so here we go. Woo! I'm going to lead you through it step by step. At any point, pause the video, say I got to this step, I didn't know what to do next, and then see if you can solve it from there. I'm going to go through it step by step. So, first thing I do is I need to isolate our variables v and dv dt. So I'm going to multiply everything by r. So I put the r over here, get rid of the r here, put the r over here. I want to isolate v, so I divide everything by b squared L squared. So this is mgr over b squared L squared. This is mr over b squared L squared. I recognize that this term is v sub t. Remember, I told you that as a hint, you want to try to get that, so hopefully you got to that point. Now, certainly you don't have to substitute as v sub t. You could leave this big mess, but it is a big mess, and so we do have v sub t as a defined variable. Might as well use it. So we have vt minus v equals mr over b squared L squared dv dt. Now I want to isolate the variables, get all the v's on one side, get everything else to the other side. So we just sort of swap vt minus v and dt. So on the left-hand side, we move this as b squared L squared over mr times dt. On the right-hand side is dv over vt minus v. Now, from this point on, this should look very familiar. We've seen problems like this before, except we have a little bit more of a complicated variable arrangement here. And so that's where the u substitution comes in, just to make it a little bit easier. So I say u equals vt minus v. We differentiate both sides with respect to t. Vt is a constant. That just is the terminal speed. So du dt just equals negative dv dt. Get rid of the dt's. Du equals negative dv, and dv equals negative du. And now we're ready to substitute this back in here, substitute this back in here, and now we're at this step here. So if we didn't quite get to this step, at this point you should definitely know what to do. So maybe pause the video, see if you can solve it from here if you didn't solve it completely yet. I definitely have confidence you should be able to do this all on your own. Okay, so I put the negative side on the a negative sign on the other side just because that's how we usually do it. On the left-hand side, there's just a constant here, so it just ends up being t times the constant negative b squared L squared over mr. The right-hand side, you should definitely recognize this as log of u. We now replace u with vt minus v. We're integrating from 0 to v, right? It started with an initial speed of 0 to drop from rest to some speed v later to get our function of v. So we substitute. Here's our final speed v. Here's our initial speed being 0, so just leaves as vt. We have a difference of logs. That's just the same thing as a division. Just to make it a little bit easier to look at, I just separated it out into the two fractions. Vt over Vt is 1. This is minus V over Vt. There's our usual solution here. And now we do e to this side equals this. So e to all this mess here, that's negative b squared L squared over mRt. That's this mess over here, equals 1 minus V over Vt. Let's swap these two sides here. So we have V over Vt equals 1 minus e to this mess. And then we multiply everything by Vt. And this is our final version. We are allowed Vt because it's defined part of the problem, although certainly if you substitute Vt with the expression for Vt, that's absolutely fine as well. Remember this mgr over b squared L squared, that's fine. I think it just makes it a little bit messier, but it's also more in terms of the original terms of the defined in the problem. Whew, that was quite a problem, but it's all steps that you can do. Everything that you did here is things that you can do. And that's quite powerful that you developed a whole system of strategies here that you solve a very complicated problem. You should be very proud of yourself.